Hello, this will be a demonstration of Proposition 33 from Book 6 of Euclid's Elements, which says that in equal circles, angles have the same ratio to each other as the arcs on which they stand, whether these angles be at the center or on the circumference. What this is going to look like is we're going to have two equal circles, A, B, C, and D, E, F. That. And they're going to have center G for ABC and center H for DEF. And we're going to have two angles standing at the centers of these. So we're going to have the angle BGC like this, BGC like this. We're going to have some other angle EHF like this. And furthermore, we'll have another angle, BAC, standing at the circumference here, like this. And we'll have another angle in the circle DEF standing at the circumference. We're going to call this EDF. Okay. Now what we have to prove is that this arc BC is to this arc EF, just as the angle BGC is to the angle EHF, and so too, just as the angle BAC is to the angle EDF. We're going to begin by making several equal arcs within these circles. So we're going to make the arcs CK and KL on the circumference of the circle ABC, such that they are equal to this arc BC. Let's do that. You do this. Euclid doesn't really explain how, but you would do this by using proposition 4.1. You would connect BC, and then you would fit a straight line from C equal to BC, and you would have that meet at point K, and you do that again from point K. You would fit a straight line within the circle ABC, which is equal to the straight line BC. So we're going to have that. And proving that gets you equal arcs is fairly easy to prove, so I'm not going to go through that. So we have the arcs BC, CK, and KL all equal to each other. And likewise, we're going to have the arcs FM and MN equal to EF, like this. Like that. So all three of these arcs, EF, FM, and MN are also equal to each other. I just realized I put two M's there and didn't make a distinction, so one of those has to be N. So again, we did that by proposition 4.1, and we proved that it's the case by, Prop 329 or 328, it's one of those two. So after having made all the equal arcs, we connect four straight lines by the first postulate. We connect the straight lines GK, KL, HM, and HN. Again, we do that easily by postulate 1. Okay. Now because the arc BC is equal to the arc CK is equal to the arc KL, right, we made all of those, all three of those arcs equal to each other in the first step. It then follows that the angle BGC is equal to the angle CGK is equal to the angle KGL. This follows from proposition 327 that on equal arcs, equal angles stand whether they be at the center or at the circumference. So on the equal arcs BC, CK, and KL, we have the equal angles BGC, CGK, and KGL upon them. Now, these all being equal, we can thus say that the whole BL is the same multiple of the arc BC, that the whole angle BGL is of the singular angle BGC, namely 3. So BL is 3 times BC, and so too, angle BGL is 3 times angle BGC. This naturally follows from their being equal to each other. So because they're equal to each other, we can have these equal multiples. So that arcs BL and arc BL and angle BGL are equal multiples of arc BC and angle BGC respectively. Now similarly, we can prove that the whole arc EN and the whole angle EHN are equal multiples of the singular arc EF and the singular angle EHF respectively. So that whatever multiple EN is of EF, the angle EHN will be that same multiple of the angle EHF. This would again be fairly easy to show by showing that these three angles EHF, FHM, and MHN are all equal to each other by proposition 327, so that arc EN and angle EHN are equal multiples of arc EF and angle EHF respectively. Now if the arc BL is equal to the arc EN, this angle BGL will of course be equal to this angle EHN. This again follows from proposition 327, where in equal circles, upon equal arcs, stand equal angles when they're both at the center. So if in these two equal circles, ABC and DEF, we have equal arcs BL and EN, then the angles which stand upon them at the center will also be equal. Again, that's 327, so that if arc BL is equal to arc EN, the angle BGL will be equal to the angle EHN. And similarly, if the arc BL be greater than the arc EN, it will of course follow that the angle BGL is greater than the angle EHN, and if the arc BL is less than the angle, or less than the arc EN, the angle BGL will likewise be less than the angle EHN. This is a simple corollary from 327. We saw a similar thing happen with prop 138. That was a proposition that said on equal bases, or two triangles on equal bases and in the same parallels are equal to each other, but from that you can easily deduce that the greater the base, the greater the triangle, and the less the base, the less the triangle. We have a similar corollary going on here, so that the corollary here goes on equal arcs, in equal circles, stand equal angles, and if the arc is greater, the angle will be greater, and if less, less. There's no specific proposition for this corollary. It's not even stated as a corollary, but it takes hardly any effort and it deduces fairly easily from prop 327, so I'm not going to go through that. Point is that if the arc BL is greater than equal to or less, is greater than equal to or less than the arc EN, the angle BGL will likewise be greater than equal to or less than the angle EHN respectively. So that these equal multiples these equal multiples arc BL, arc EN, angle BGL, and angle EHN have this situation about them such that if one arc exceeds the other, the one angle will exceed the other angle, and if equal, equal, and if less, less, which means that these equal multiples satisfy the condition for proportionality as laid out in the fifth definition of Book 5. Right, because we noted that the arc BL and the angle BGL are equal multiples of the arc BL and the angle BGC respectively, and likewise that the arc EN and the angle EHN are equal multiples of the arc EF and the angle EHF respectively, so that because these equal multiples have this situation about them as stated in step 4, we can thus say about the magnitudes themselves, of which they are equal multiples, that as the arc BC is to the arc EF, so the angle BGC is to the angle EHF. Furthermore, we know that the angle BGC is double the angle BAC, and likewise that the angle EHF is double the angle EDF. This follows from proposition 320, which says that on the same arc, if you have one angle standing at the center of the circle and another angle standing at the circumference, or the part of the circumference that's not the given arc, the angle at the center will be double the angle at the circumference. That's exactly what we have going on here. That the angle BGC is double the angle BAC, and likewise the angle EHF is double the angle EDF, which means by proposition 515 that multiples have the same ratio, or equal multiples have to each other the same ratio as their parts, so that as the angle BGC is to the angle EHF, so the angle BAC is to the angle EDF. But it was also shown that the arc BC is to the arc EF, just as the angle BGC is to the angle EHF, which means we have two ratios which are the same with the same ratio, which means prop 511, they are the same with one another, so that we can say that the arc BC is to the arc EF, just as the angle BAC is to the angle EDF. And this is all that we set out to prove. We set out to prove that the arc BC is to the arc EF, just as the angle BGC is to the angle EHF, and so too, just as the angle BAC is to the angle EDF. And having proven all of this by now, we are thus done with the proposition, therefore, etc. QED. This type of argument, it parallels very nicely to proposition 6.1, which is the first prop of this book. This method that Euclid uses to prove that four magnitudes are proportional is quite common. And this is done by having them laid out in the given, making their equal multiples, showing that these equal multiples have this situation about them, such that if one exceeds the other, the third will exceed the fourth, and if equal, equal, and if less, less. And having proven that, then using definition 5.5 to say something about the magnitudes of which they are equal multiples. This is the second time we've seen this general form of an argument, and we'll see it a few other times throughout the Elements, even as late as book 12. So this kind of argument, you should know it. It's quite common, it's quite easy to do, and it's very useful. We've already proven two very kind of neat and important things using it, and we'll come to prove yet more important things using it. Now, though the text of the proposition, though the original text of Euclid ends here, often you'll see another statement appended to the enunciation that says, as the arc is to the arc, and as the angle is to the angle, so the sector is to the sector. So that in equal circles, the angles have the same ratio to each other as the sectors in which they stand, or as the arcs which contain them. This is, I believe, is credited to Theon of Alexandria. It's very common to see this part of the proposition used. It's not something Euclid wrote himself, but it's very important. You'll see it in Ptolemy, for example. He uses it. So it being a part of the enunciation that is so widespread and honestly important, I will actually include a demonstration of this last part of the enunciation of this addition to Prop 633 before I close out the video here. So I'll end the first part of the video here and move on to proving this about the sectors in equal circles. Now, before I move on to the extension of proposition 633 concerning the sectors of equal circles and the ratio those have to one another, I first have to cover a lemma that in equal circles, equal angles at the center stand inside equal sectors. There's no propositions in book 3 about sectors, so this lemma is in order. We're going to have two equal circles, A, B, C, and D, E, F. And just like last time, they're going to have the center G and the center H respectively. And at the center G, we're going to have some angle stand, namely BGC, like this. And we're going to have an equal angle stand at H, and this is going to be the angle EHF. So that the angle BGC is equal to the angle EHF. And given this, that the two circles, ABC and DEF, are equal to each other, and that the two angles BGC and EHF standing at the center are also equal, I say that this sector, BGC, is equal to this sector, EHF. We're going to begin by taking just any point on this minor arc, BC. We're going to call it just K, very simply. And similarly, we're going to take a random point on the minor arc EF. We're going to call it L. And now we're going to join 10 straight lines, all by postulate 1. We're going to join BC, BA, CA, BK and KC. And now on to the next circle, EF, ED, FD, EL, and FL. Now, because the angle BGC is equal to the angle EHF, we were given this information, and that the radius BG is equal to the radius EH, and so too the radius GC is equal to the radius HF. We know this because the two circles are equal in definition 3.1. The definition of equal circles are those who have their radii equal. So BG, or the radius BG, is going to be equal to the radius EF in the equal circle, and so too the radius GC is going to be equal to the radius HF in the other equal circle. Which means that between the two triangles BGC and EHF, we have one angle equal to one angle, and the sides containing the equal angle equal as well, which means by proposition 1 for the side angle side congruency theorem, these two triangles BGC and EHF will be equal in all respects. First, in area, that the triangle BGC and the triangle EHF will be equal to each other simply, and also that the base BC is equal to the base EF. Now, because the angle BGC is equal to the angle EHF, it of course follows by a property of magnitudes that their halves will be equal as well, right? Halves of equals are equal to. But 1/2 of angle BGC is the angle BAC by proposition 320, that if on the same arc you have one angle standing at the center and a second angle standing at the circumference, the angle at the circumference will be half that of the angle at the center. So the angle BAC is half the angle BGC, and so too the angle EDF is half the angle EHF. And again, halves of equals being equal as well, we can say that the angle BAC is equal to the angle EDF. Now, if we just look at one of these circles, let's just take the circle ABC, we have a cyclic quadrilateral, a quadrilateral, all of whose points lie on the circumference of the circle. In this case, we have the cyclic quadrilateral ABKC, and we know by proposition 322 that the opposite angles of cyclic quadrilaterals add up to two right angles, which means that angle BAC plus its opposite, angle BKC, add up to two right angles. And so too, in the circle DEF, we have the cyclic quadrilateral DELF, which means that its opposite angles also add up to two right angles, namely that the angle EDF plus the angle ELF adds up to two right angles, and we have two sums of angles which are equal to the same thing, namely two right angles, common notion 1, they are equal to each other, which means that angle BAC plus angle BKC is equal to angle EDF plus angle ELF. But we had shown above that the angle BAC is equal to the angle EDF, which means by common notion 3, if we subtract these equals from the whole equals, the remainder so gotten will be equal as well, which means that the remaining angle BKC is equal to the remaining angle ELF. Now, being equal, these two angles BKC and ELF being equal, it then means that the two segments BKC and ELF are by definition similar segments. That's definition 311, which is the definition of similar segments. Those, the angles in which are equal, segments wherein the angles are equal are similar segments. So the segment BKC is similar to the segment ELF. And furthermore, the two segments BKC and ELF are on equal straight lines. And we know by proposition 324 that similar segments of circles on equal straight lines are equal in area to each other. So the segment BKC is equal to the segment ELF, But it was shown above that the triangle BGC is also equal to the triangle EHF, which means by common notion 2, if we add these equals to those equals, the wholes so gotten will be equal as well, so that the triangle BGC plus the segment BKC will equal the triangle EHF plus the segment ELF. But the triangle BGC plus the segment BKC is obviously the sector BKC, right? The sector BKC is this pizza slice looking thing to make it very obvious what exactly I'm talking about. The sector BGC here is then equal to the sector BGC is obviously the triangle BGC plus the segment BKC. And again, the triangle EHF plus the segment ELF is obviously just the sector EHF, which means that the sector BGC is equal to the sector BHF. And in these sectors stand equal angles, which means we have proven that which we set out to prove. In equal circles, equal angles at the center stand inside equal sectors, namely that because the circle ABC is equal to the circle DEF, and in it, the angle BGC at its center is equal to the angle EHF at its center, we wanted to prove that the whole sector BGC is equal to the whole sector EHF, and we have thus proven this, so that means we are done with this lemma, therefore, etc. QED. This lemma is necessary to prove this extension of proposition 633, that in equal circles, as the angle is to the angle and as the arc is to the arc, so the sector is to the sector. So having proven this necessary lemma, I will move on to complete proposition 633. So now we are ready to tackle and prove the extension of proposition 633, which says that in equal circles, the angles and the arcs have the same ratio as their sectors. I'll be using the same construction that we made in the first part of 633, so I won't be going through any of the construction at this point in the video, nor have I set out for us the given because we already have it, but I have laid out a specification, and that is, what we're going to prove is that the sector BGC is to the sector EHF, just as the angle BGC is to the angle EHF, and just as the arc BC is to the arc EF. Now, we had shown in the second step of this proposition that the angle BGC is equal to the angle CGK is equal to the angle KGL, which means by the lemma, which I had shown before this, that in equal circles, equal angles at the center stand inside equal sectors. We can thus say, because these three angles are equal, the sectors BGC, CGK, and KGL will also be equal to each other. Again, that's by the lemma, which means that the whole sector BGL, which is this sector right here, is the same multiple of the sector BGC that the whole angle BGL is of the angle BGC. Now, similarly, we can prove that, or we can show that the whole sector EHN is the same multiple of the sector EHF, that the angle EHN is of the angle EHF. Now, if the angle BGL is equal to the angle EHN, it then follows again by the lemma, which I had shown before this, that the whole sector BGL is equal to the whole sector EHN, because these are equal circles, which means that equal angles stand inside, or equal angles at the center stand inside equal sectors, so that if the angle BGL is equal to the angle EHN, the whole sector BGL will be equal to the whole sector EHN. And furthermore, if the angle BGL is greater than the angle EHN, it then naturally follows, it easily follows, that the whole sector BGL will likewise be greater than the whole sector EHN. And finally, if the angle BGL be less than the angle EHN, it of course follows that the sector BGL will be less than the sector EHN. which means that these equal multiples, these four equal multiples, the sector BGL, the angle BGL, the sector EHN, and the angle EHN have this situation about them of alike exceeding, alike being equal, and alike falling short, which means that they satisfy the condition of proportionality as laid out in definition 5.5, right? Because the sector BGL and the angle BGL are the same are equal multiples of the sector BGC and the angle BGC respectively, and likewise the sector EHN and the angle EHN are equal multiples of the sector EHF and the angle EHF respectively. And again, as proven in the ninth step up here, because they have this situation about them, we can thus say by definition 5.5 that as the angle BGC is to the angle EHF, so too the sector BGC is to the sector EHF. But it was shown in the fifth step of this proposition that as the angle BGC is to the angle EHF, so the arc BC is to the arc EF, which means we have two ratios which are the same with the same ratio, which means they are the same with one another. So by 5.11, we can finally say that the sector BGC is to the sector EHF, just as the arc BC is to the arc EF. And this is all that we had set out to prove, which means we are done with the proposition, therefore, etc., QED. And that marks the end of book 6, which ends for a while the geometric portion of the elements. A classical way to group the 13 books of Euclid's Elements together is to put the first 6 books in their own category, and then with the last 7, you either put 7, 8, 9, and 10 into their own category, and then 11, 12, and 13 into a third category, or you put 7 through 13 all in the same category. The point is that this end of book 6 right here marks a turning point in the elements, and so too it'll mark a turning point in this channel and the videos it produces. So for a while, we'll be on number theory. That's the next 3 books, 7, 8, and 9. And then on book 10, we'll talk about commensurable magnitudes, commensurable and incommensurable magnitudes, of course. And then the last 3 books of 11, 12, and 13 will be about solid geometry. So yeah, I'm very happy to be done with this first part of the elements. I appreciate you for sticking along with me for this ride. I've been working really hard on this channel, so it means a lot that it means a lot that you support me and that you watch these. So with that, I'll end the video here and move on to proposition 7.1.